Well, good morning. Thank you again for joining us today. We're really excited about today's session and thanks for your patience. We are a couple minutes behind getting started, but we're really looking forward to today's session and to hear from our 2021 Edith and Peter O'Donnell Award recipient in engineering. My name is Terrence Henry. I'm the Executive Director of TAMIS. That's the Academy of Medicine, Engineering, and Science of Texas. And before we begin today's research presentation, I'd like to tell you a little bit about our organization. TAMIS supports cross-disciplinary collaboration to advance research, innovation, human talent development, and business in Texas. We are composed of more than 320 Texas-based members of the three national academies. That's the National Academy of Sciences, National Academy of Engineering, and National Academy of Medicine, as well as the state's 11 Nobel laureates. And we're supported by the founders of our endowment, and we'd like to take a moment and thank them for their support, and as well as our 18 academic and medical research member institutions. We want to recognize them and thank them for their ongoing contributions to our research community and to the health and vitality of our state. Today's session is the second of 4 that are highlighting the research of this year's recipients of the Edith and Peter O'Donnell Awards. These awards play a vital role in recognizing and promoting rising star researchers in the state. The awards are named in honor of Edith and Peter O'Donnell, who have been steadfast supporters of TAMIS since our inception and incredible advocates for excellence in education and research. The awards are supported through the O'Donnell Endowment, and we have some of the supporters of that endowment listed here. We'd like to thank the donors to that endowment, as well as the O'Donnell Foundation, for their generous contributions to the awards program. We'd also like to thank our O'Donnell Awards Selection Committee, which does the very hard work of reviewing and selecting the candidates and awardees for the awards each year. We have 12 TAMIS members that serve on 4 subcommittees for these awards. There's one for each award. And last year it was chaired by Mr. Kenneth Arnold. We want to thank him and the committee for their hard work. We'd also like to thank all of the Nobel laureate committee members who reviewed the finalists for these awards. Today's session will be a 45-minute session. We'll have a 20-minute presentation from the recipient of the Engineering Award, Dr. Guihua Yu. And after Dr. Yu concludes his presentation, we'll have time for audience questions. We really encourage you to submit questions using the Q&A box, which is located at the bottom of your Zoom window. You can type your question in there, and we'll get to it during the Q&A portion of the session, which again will happen after the presentation. But please feel free to submit your question using that Q&A box at any time during the session. I'm now very happy to introduce our moderator for today's session. Her name is Dr. Joan Brennicke, and she is the professor and Cockrell Family Chair in Engineering number 16 in the Department of Chemical Engineering at the University of Texas at Austin. Dr. Brennicke is a TAMIS member from the National Academy of Engineering and also served on the 2021 O'Donnell Awards Committee as the Engineering Subcommittee Chair. So Dr. Brennicke, thank you so much for your service to TAMIS and for moderating today's session. We'll now turn it over to you.
All right, great. Thank you so much, Terrence. It is really my pleasure to introduce Dr. Guihua Yu today. Dr. Yu is a professor of material science and mechanical engineering here at the University of Texas at Austin. He received his doctorate from Harvard University in 2009 after graduating from the University of Science and Technology, China, with highest honors in 2003. He did a postdoc at Stanford University before joining UT Austin in 2012. Dr. Yu's research focuses on the design and synthesis of functional nano-architectured materials, particularly organic and hybrid organic inorganic nanomaterials, fundamental understanding of their chemical and physical properties, and development of large-scale assemblies and integration methodologies to enable their technologically important applications in energy, the environment, and sustainability. Dr. Yu has received numerous awards, including the TMS Grimakombe Medalist Award, the IUPAC Award for Creativity in Applied Polymer Science from Polymer International, and Outstanding Young Scientists by the World Laureates Forum. He was selected for the O'Donnell Award in Engineering for his revolutionary use of nanotechnology and conductive polymer hydrogels to provide solutions to two of society's biggest challenges, water sustainability and energy storage. Dr. Yu's approach of looking at organic nanomaterials and understanding structures down to their smallest scale has led to the creation of new multifunctional polymeric nanostructures and hybrid organic inorganic nanomaterials with really unique physical properties that can be applied to improve efficiency and function. So please join me in welcoming Dr. Guihua Yu.
Thank you so much, Joan, for a very kind introduction. Can you all see my full screen?
Looks perfect.
Okay, great. Thank you. All right. So let me get started with the most important slide. I would like to thank Tamis first, and also the O'Donnell Foundation and the O'Donnell Award Selection Committee for this very honor and very incredible honor and award. So I always start with the most important slide of acknowledgement, because without the support of many people that have been involved in the past years, I wouldn't be here to share like our exciting research with you. So over the past 8 years at UT Austin, I have been very fortunate to have worked with over 70 outstanding undergraduate and graduate researchers, postdocs, and visiting scholars. It's really them who make all the exciting research possible. And this is actually a great recognition of this wonderful group I have the honor to work with. So I would like to thank all like my current and former group members. And also I'm very honored and very kind of grateful to have many wonderful collaborators, both at UT Austin and at other university and the national lab. So this slide shows their name. I would like to give a special thank to Dr. Goodenough and Dr. Manthran. So both of them are my collaborators, the colleagues, and also my great faculty mentors. And many thanks to Dr. Johnston for leading the nomination for me. And then also my funding support for my research program in the past years, especially the Department of Energy, DARPA, and Lockheed Martin and National Science Foundation for this part of energy hydrogels I'm talking about today. So hydrogel, as we all know, are usually jelly-like solids with elastic nature. They are commonly recognized in our daily life, such as baby diapers, the contact lenses, and they previously have been found significant applications in tissue engineering, drug delivery, and other biomedical applications. And if we're looking into hydrogel at from a more fundamental molecular level, they are highly cross-linked network capable of containing large amount of water and maintaining these 3D hierarchical structures. And their building block can actually ranging from the polymer, carbon materials, inorganic compounds, and their cross-linking mechanism can be through the chemical bond or the physical interactions. And then since starting at UT Austin, so we have been working on to develop a class of highly synthetically tunable nanostructured conducting polymer hydrogel. So they are hierarchical porous, structurally tunable in size, morphology, porosities. And then these tunable elements for gelation includes the basic building blocks, different cross-linking mechanism to the right, and you can see also involving functional additives. So this actually is the powerful gelation chemistry endows these different hydrogels with very tunable physical-chemical properties. And these properties actually can be integrated into various materials, various components, and then to go beyond their exciting applications beyond about biological in energy storage, conversion, and sustainable clean water productions. And today I'm going to list several examples. So in addition to the synthetical tunability, and the micro and the nanostructure of hydrogel can be explored as both precursors and templates for architecting these 3D framework of electrochemically active materials. And then these very unique interconnected porous structures, let me bring my pointer up. So these very unique 3D interconnectivity porous structures of hydrogel and hydrogel-derived materials, they can actually enable fast charge mass transport while offering these large surface areas and they actually can be regulated in terms of polymer-water interactions to achieve desirable water retention, absorption, and evaporation for water-related application. So we actually have been exploring these various applications in energy storage conversion, solar water desalination harvesting, and as the responsive adaptive materials. I will start with the two examples on how synthetically we can tune these class of materials. So the first example is 3D hierarchically porous structure conducting polymer hydrogel. So here we use this polyaniline as an example. So this is polyaniline is very special. They have the alternating these single and double bonds. So that gives them the good electronic conductivity. And then we actually study these various of the factors, including this fatty acid as both dopants and then cross linkers. So this fatty acid is naturally abundant materials that exist in nature in plants. So you can see they are highly phosphoric acid group populated. So they can serve as the cross linker to cross-link polymer, these polymer monomers. And then they are the three level of hierarchical pores involving from this micron size to this gap size. So this is about tenths of a nanometer, and this mesh size is intermolecular chains. And you can see from this scanning electron microscopy and then also the transmission electron microscopy. So they are highly this coral-like dendritic nanofiber with a diameter around 50 nanometers. And these TEM images really clearly show they are highly continuous, interconnected framework. And then we can tune their surface area from tens of to hundreds of square meter per gram. And then their electronic conductivity based on this conducting polymer can also range from a few to 1,000 Siemens per meter. So the next example is by rational selection of different dopants. So we can explore this supermolecular self-assembly mechanism. So this is one example using the polypyrrole, which is known to be very difficult to form nanostructure. They typically prefer to form this particle-like due to their branch and cross-link chains. And then if we select this tetrafunctional group copper persulfate cyanate, so they can actually forming these 1D nanostructures. This is a highly interconnected network of 1D nanowires. So you can see from this mechanism wise is this tetrafunctional group, they can actually serving a spherical kind of disc-like shape. That tetrafunctional group enable the supermolecular self-sorting mechanism. So it's the first time in literature that use without the need of the templates, they can form this highly 1D nanowire, but it's interconnected network. And then when you change the different cross-linker, for example, from this tetrafunctional group to the two functional group, it's indigo, to the quarter of the size, this monofunctional group. So you can see the clear transition from this 1D nanowire to this 1D nanoparticle assembled necklace to these 3D nanoparticle clusters. So you can see the supermolecular self-sorting mechanism, it actually can play a very effective role in terms of controlling their structure and morphology. And moreover, the nanostructure, the confinement effect due to this formation of fiber, they give very different physical properties. So one example is electronic conductivity. So if you're using this copper per CuPCTS, they can give about 8 Siemens per centimeter, so it's 800 Siemens per meter. And if you use isotene or pristine polypyrrole, so they are 2 orders lower in terms of electronic conductivity. So let me show you how these synthetically tunable structures of the conducting polymer hydrogel can be used. So we actually first explore their applications in electrochemical energy storage. As we all know, electrical energy storage continue to be essential to realize our society future energy economy to achieve a secure and sustainable energy supply for all the people. And then the upper right figure shows there are a number of the energy storage technology potentially useful for the high value application from EVs to the grid integrations. And then you can see here, the lithium ion battery is the dominant one, is the prime champion, given their both high energy and power densities. And the commercial lithium ion battery are currently based on lithium intercalation compound using intercalation mechanism. So basically it's lithium ion shuttles between the two host structures serving both as anode and cathode materials during the battery charging discharging. And we can see energy density is related to both capacity and also the voltage. So to achieve a higher energy, we need to have higher capacity or higher voltage battery electrode materials. And then several key parameters to evaluate energy storage technology shown in this slide. This is so-called Regonian plot. So basically it's plotting the comparison between the power versus energy. So if we take electrical vehicle as an example, so power means how fast your car can accelerate it. And the energy density per weight or per volume means that per charge, how long your car can actually go in terms of mileage. So if we want to improve the wider use of the electrical vehicles and then grid scale integration, so we really need to have both high power and also high energy densities. In addition, we also need to have a better cycle life to be able to use it for longer cycles. We also need to have the more safe batteries, and the cost is also an important factor too. So let me show you how the conducting polymer hydrogel can play a very important role in making next generation high energy power batteries. So if we look into the traditional electrodes in lithium-ion batteries, so there are three components. So these are the electrode particles, and then actually bind it with the conducting polymer, the conductive additives, typically is carbon particle, and then the blue color actually shows is these non-conductive binder polymers. So you can see this is not really ideal because the electron are typically conducted through these chains of particle through the composite, and then it's quite randomly distributed. So many of bottle network and pool contact actually will go in between these different inhomogeneous phases. And then for traditional battery with a very limited kind of structural change electrode, so it's not a big problem. But if we wanted to make the higher capacity next generation battery electrode to work, so this will become problematic because during battery charging discharging, the structural change of the electron particle actually will make the electrical contact quickly lose. So if we look into this conducting polymer, sorry, wait, changing too fast. So the conducting polymer hydrogels we develop actually have these very important features. They can offer larger surface area. They have very good electronic conductivity, and also they have good ion accessibility. So they can actually make the next generation higher capacity electrode material to work. So how it actually work? So if we look at back the microstructure of the gels I showed you before, so they are these three different levels of porosity involved. Micron size, you can accommodate micron size particles. And then you have this gap size that's actually you can accommodate nanometer size of particles. And this conducting polymer hydrogel is a very powerful framework electrode because they can give in several important functions. So during the duration, so these particles can be coated with a layer of conducting polymer layer. And not only they can form in this gel network, we call it apple tree design, they can avoid this particle kind of aggregation. So they can make the more effective use of each of these electrode particles. And so we use this as one example. We make this magnetite, which is the iron 304. So it's very abundant in nature, and they have a theoretical capacity 3 times as high as the current graphite, commercial graphite anodes. But they are electrochemically very sluggish due to this very tedious process of the intercalation, conversion, and then reconversion. So it's very challenging to make this material work. So we demonstrated this gel, the iron 304, this magnetite particle, so with the layer of polymer coating and then well separation between the particles. So by the control means that a conventional method to make it, and then these are like synthetically tunable conducting polymer hydrogel. So you can see under this different C rate. So 2C means that's 30 minutes charging, 0.1C means the 10-hour charging discharging. So you can see this magnetite particle actually can work right now with a very minimum amount of conducting polymer gel, about 10 to 15 weight%. So the control, you actually need to over 40%, but still at a higher rate. So they actually have very small kind of capacity you can utilize. And this framework actually is general for various of these high capacity, ultra high capacity electrode. So for example, we also explore the gel with silicon. So you can see the different mixing methods also yield to very different results. If we go with conventional PVDF, so this is a conventional binder with a silicon, so it quickly decay due to this very big structural change of silicon particle. But if you just physically mix, it's work better initially, but quickly decay. When you have these 2 levels of interconnectivity, they are very stable, and they actually have about 5 times capacity increase compared to the current graphite materials. The same applies to the cathode. It's actually very, as future generation cathode materials, they have also high theoretical capacity. So we actually use the gel to combine with the lithium sulfide and sulfur, so they can actually work very stably. And then another example I'd like to show is for solid state batteries. So this is very actively researched areas. And then the solid state battery actually have the potential better safety and stability. So they can remove the flammable liquid electrolyte, and then the solid-solid interface actually potentially can enable higher cycling stability and have better kind of suppression of the dendrites. But still, there are many challenges remain in solid state battery, including how to effectively suppress and avoid delamination of lithium metal. And then also this solid-solid interface, it will lead to the higher internal resistance, so make the high rate, high power very difficult. Conventionally, there are two types of materials for a solid state electrolyte, the key components for solid state battery. One is called inorganic solid electrolyte, which is typically ceramic materials, for example, lithium lanthanate titanate, LLTO, or to have a better kind of handleability, because ceramic typically is more fragile. So people actually trying to explore composite polymer electrolyte, which is a composite of both inorganic filler of ceramic, have better ionic conductivity, but also with some ionically conductive polymers. So with this composite, you can, even with a little bit lower ionic conductivity, you can actually make the interface, it's more intimate to have a higher rate possible. But they actually have a significant challenge, because when you wanted to combine this inorganic filler with the polymer at a higher concentration, so often you will see is you cannot go monotonically increase in terms of ionic conductivity. So with certain range, so you will start to see this plateau of ionic conductivity. So this actually is resulted from this aggregation of these inorganic fillers. So that actually will lead to the deterioration of ionic conductivity, even with more ceramic fillers. So we actually try to explore the structural advantage of these interconnected, highly porous conducting polymer hydrogel as a template. So you can mix this ceramic precursor with the polymer precursor, and instead of you have this nanoparticle random network you want right now, you can form this pre-percolated network. So you can have a higher ionic conductivity and a better electrochemical stability. So this is SEM showing these interconnected ceramic fillers connected through the hydrogel network, and it's very flexible to work with. And you can see from our electrochemical characterization with this different type of mechanism. One is with the gel framework, and then these random particles and other control samples. So you can clearly see our gel-derived framework offer the highest ionic conductivity, and then the percolation is actually at much higher volume fraction. So we can actually achieve the desirable room temperature 10 to -4 Siemens per centimeter for solid state batteries. So let me use the next about 10 minutes to talk about other application. So this is really kind of our recent 2 or 3 years efforts that trying to address the water sustainability. As we all know, water covers over 70% of Earth, but very limited amount we can use. And typically, so when we try to make the seawater possible as a possible water source, so the two major industry desalination technology are either based on thermal-based process. So for example, this is multi-stage flashing or multi-effect desalination, but they actually often involve high energy consumption and then a very large infrastructure needed. And the membrane is also another very promising technique, but they also have some limitation. They usually require the high pressure, especially working with the salty waters. And then the cost of membrane is relatively high, and it's prone to the biofoulings. And another thing is these thermal desalination plant needs a significant amount of energy. So they actually need about over 20 kilowatt hour of electricity to produce a cubic meter of the water. And then for the RO reverse osmosis membrane, sometimes you also need to have a 2 to 3 kilowatt hour electricity to produce 1 cubic meter of the water. So as water is essential resource for life, and then it's intricately related to energy. So how to effectively utilize renewable energy for producing clean water is another grand challenge. And then solar vapor generation technology is actually one of the promising techniques. And then you utilize the solar sunlight as the only energy input, and then heat up to evaporate the water So it's called solar steel process. But currently, the challenge is the diffusive solar energy make the energy, it's not enough for making the water, effective water evaporation. Oftentimes requires expensive solar concentrator to be involved to have the appreciable evaporation rate. And the interfacial evaporation later becomes a very effective design. And this is where you can utilize nanostructural materials to have this localized evaporation at the surfaces. So the three key important design is you need to have both high solar absorption, and also you need to have very high heat localization at its interface. And then you have plenty of water transport going from the bulk to interfacial. So you can actually minimize the energy loss during the process. And then previously, in the solar vapor generation field, there are two general methods explored. Typically, it's using different type of light absorbing materials, can be carbon-based or semiconductor nanoparticles, or changing the structural design involving some of these self-assembled monolayer particle, have the nanoplasmonic effect to enhance the solar to light absorption, or bio-inspired structure to effectively use this 3D architecture from the wood to improve the solar evaporation rate. But generally, they have limited the rate to about 1.5 kilograms of water per square meter of the active materials per hour operation. So recently, we discovered the hydrogel is very promising class of material for solar vapor generation. So they can offer this highly tunable water polymer interaction to effectively reduce the energy need for the water evaporation, basically changing the latent heat of water evaporation. So in our first work demonstration, so we utilize these hybrid gels. One is this hydrophilic polyvinyl alcohol gel, and this is serving as hydrophilic polymer network. And the polypyrrole is a semiconducting polymer, so they can effectively absorb sunlight and locally heat up these molecular mesh. And then due to this reduced energy needed for water evaporation, so they can actually have to achieve very promising the features. So one of the key features in here is this regulatable, the hydrogel water kind of interactions. As we know, hydrogel is 3D cross-linked polymer network saturated with water. So they are the three different water states involved in the system. So you have the free water showing here, and the intermediate water is in between the free and least closely bound water. So this intermediate water actually requires less energy to evaporate. So that experimentally observed in our system before, but we demonstrated the first time using the hydrogel for these anti-fouling solar vapor generation. So given this structural design, so we can enable this very long-term water desalination with record high solar evaporation rate. So we can achieve over 3 kilograms of water per square meter per hour of evaporation rate. And this, you can see effective removal of the salts with various salt concentration, Baltic salt and world salt and the Dead Sea. So you can see the over 4 to 5 orders of the salt can be removed, and then the distilled water is actually more than meets this drinkable water criteria. And then we demonstrated in a prototype solar water purification system, we put on our engineering teaching center building, ETC building, to produce this potential daily yield over 20 liters per square meter a day. So it's enough for like a household of 4 people. And later the Science magazine actually highlights our work. And in the recent 2 years, we have expanded this direction through the more systematic studies, and then to show the hydrogel are very tunable material platforms for the solar water purification. So we actually, for example, we better understand the solar absorptive absorptive particle interaction to enable this energy nano confinement. And we also can tune this hydrophility of the polymer network, by changing the functional group or by a selection of different hydrophilic polymers. And then we also investigate different effects, for example, surface topology or surface wettability to enhance the solar vapor generation efficiency. And then right now we are working on to develop a more prototype closer to use the devices to be able to hopefully to be able to use for the household needs and potentially even larger scales. So let me give you the last example. So this is a very recent 2 years work. So not only solar water desalination is a way to mitigate water needs, but also atmosphere water harvesting is another very promising technology to utilize the water vapors existing everywhere. So typically fog and dew technology are more used before, because these fog harvesting typically can use the larger nets or meshes to catch these smaller water droplets. Dewing is actually you kind of like refrigerate the air below the dew point to condense water vapor. But these two techniques have limitation of both geographical or climate conditions. They typically need to have the right temperature and humidity. But moisture harvesting from the ambient air everywhere is more promising in terms of wider applicability to the worldwide needs. So typically, there are several types of these functional materials for moisture-based absorption. So for atmosphere water harvesting, for example, silica gels, these are like porous materials, zeolites, or hygroscopic salts such as lithium salt, or like these other metal compounds. And then very recently, this metal organic framework material also has been explored for the atmosphere water harvesting. So due to their very highly tunable structure between the metal ions and these organic ligands, so they can offer very tunable the pore size and pore volume to have tunable absorption behavior. So they can actually have a high absorption capacity at even very low, extremely low relative humidity. But one of the limitations for all these different type of material is when you talk about releasing water, you need to pay the penalty, because high affinity to the water also means that when you want to release them to dissolve the water, you need to have the high energy involved to release this water. So you need to have a delicate balance between these two. So we actually recently developed this, we call it super moisture absorbent gel, SMAC, for atmosphere water harvesting. So this is a hybrid of two components. One is hygroscopic polymer, is chlorinated polypyrrole. The other is the thermal responsive hydrophilicity switchable polymer, is polynipan. So this interpenetrating network can give you both high absorption of water, but also due to this liquid to liquid liquid transition, so you can effectively reduce this barrier for the desorption. So you have much more efficient water release. So this is our design. We use polynipan as thermal responsive polymer network, and then chlorinated polypyrrole as this hygroscopic salts to absorb the water vapor. So they are highly porous from the SEM image you can see. And this is where the mechanism I'm going to show you quickly. So basically during this water capturing, hygroscopic polymer can absorb the water vapor, and the water, due to the internal water transport between the hygroscopic to this nipan, they can have better storage capacity. And if you, with the mild temperature change, for example, by mild sunlight, so you actually can effectively induce this release of the water by this hydrophilicity switching, because of their like lower critical solution temperature is actually can actually change their hydrophilic state, hydrophobic state, so they can release the water effectively. So in our optimized design, so every hour, so you have 15 minutes absorption, 10 minutes release. So you can see, so on average, so we can have the solar powered atmosphere water harvesting with the water yield potentially about 20 to 40 liters per kilogram of these active gels, SMAC gels, depending on different relative humidity. And very recently, we explored this SMAC gel to actually make the impact on the soil for the sustainable agriculture. So basically, we mix these SMAC gels with very sandy soil. So you can actually make these self-watering soil. They can harvest water from the air and provide water to the plants upon solar heating. So it's really kind of mimic the nature cycle. So when at a cold night, you absorb the water at the warmer temperature at daytime. So you slowly release the water. So in our initial demonstration, we found that compared to the sandy soil, so even with significant irrigation, after 2 days, so you barely have this radish to be able to grow. But with our SMAC gel, without the need of the irrigation, so they can self-stain, they can even actually work for over like a few weeks. So this is actually one of the potential application of our SMAC gel demonstrated for a different application. So let me stop at this acknowledge slide and then take any questions that you may have. Thank you for your attention.
All right. Thank you so much, Guihua, for a really fascinating talk, especially with all of the potential applications of these engineered hydrogels. Um, as Terrence said, we would like you to enter your questions in the Q&A box. And in fact, we've already got a question for you. And this is actually about the last thing that you talked about. For the hydrogels in the soils, what happens to the things besides water, right? So have you looked at potential nutrient management properties of the gel in addition to the water availability for the plants? So can the gels also act to manage fertilizer release for plants?
Thank you so much, John, and then thank you for this wonderful question. So due to, I think due to the time limits we have, because we only just demonstrated the SMAC gel self-watering soil for the agriculture kind of use just last summer. So we haven't got into the nutrient part, but I think we really anticipate that with this slow release, just like hydrogel for slow release of the drug, so potentially we can incorporate these like these agrochemical into the system. So not only can slowly release the water, but can slowly kind of release the agriculture kind of chemicals too. So that can actually also be very important, having to minimize these land desertification and also the degraded kind of land use. So I think that's possible, but we will definitely try it in a very near future.
Okay, great. We'll look forward to those results. Then there's some just very enthusiastic comments about what great work this is. But we've got a question here. How does the membrane separation for desalination correlate with solar evaporation, compare with your solar evaporation method?
So it's a great question. So our old system right now is actually kind of quite promising, also relatively mature. So we actually, but generally they actually offer it's in an intermediate level. So in terms of thermal, it's more for bigger infrastructure, larger use, centralized use, and RO actually can be relatively smaller scale. But due to this like the fouling problem, so we see, and also due to the smaller kind of needs, potentially for the more household needs. So the solar vapor generation, I think it in terms of the technical adaptability, so they do have some kind of advantage. But in terms of RO system, in terms of efficiency, if it's not very salty kind of water, I think they have an advantage and also easy to use. And the solar vapor generation, if we can make it very efficient using only natural sunlight, I think it's also very promising, because for the disaster hit area like Houston and Texas and many other kind of states. So if we have the solar vapor generation kind of system, so basically you can work with various different different source of water, even kind of wastewater. So because of solar steel, the process it's generic to produce distilled water.
Okay, great. Kind of a general question here, which I'm kind of interested in, is do hydrogels occur in nature?
Pardon?
Do hydrogels occur naturally in nature?
Oh yes, I think the hydrogel oftentimes also is called kind of from point of view is kind of a nature inspired platforms for some chitosan and naturally forming some of these gel form of materials. It is true that the hydrogel is both nature inspired and also kind of bio inspired materials.
Great. Okay. Yeah. So yeah, they are kind of bio inspired. Question about whether there's any possibility of the, what's the integrity of the gels? Can the gels actually elute out in this, for instance, the released water?
So over the testing period, we tested it over a few weeks to months. So in terms of structural integrity, so these gels remain quite stable. And also in terms of the fouling the problem, so we also found that even at higher like a salt and also in more nature, the creek water in close to ETC and our ERC. So we try is under these natural operation conditions. So they are mechanically stable, and also they are kind of functional wise, they also remain stable, at least in terms of a month.
Okay. Question about the thermal conductivity of the hydrogels. Have you measured those, and is there any potential for using them for thermal insulation applications?
It's a great question, Lee. So we haven't tried that, but I think the thermal conductivity really depends on what type of the hydrogel, kind of your polymer, what type of polymer you use for hydrogel. And then people use these like aerogel, right? When you remove the water, the aerogel. So it's actually very popular. You can use inorganic aerogel, you can use polymer aerogel. So they can be used for the thermal insulation applications.
Question, how expensive?
Yes, yeah. So in terms of the cost right now, for example, if we're talking about very large scale use for agriculture needs, so our SMAC gel, because involving some relatively expensive components, so we are working with like a more kind of a cheaper version of raw materials. So right now it's still relatively expensive. So I think we did, my student and I did an estimation. I think right now probably it's not practical for like a large scale the agriculture need use yet, but for the solar vapor generation, so because it's efficiency, high efficiency, so we can potentially make it to like household needs for sure.
And kind of, I guess, related to that is, what's the, where are you in terms of commercializing these hydrogels for use in these various applications?
Yes, so we are not only working on advancing kind of the technology by developing more better materials, and also we are also kind of working with some of our industry partners, for example, trying out the SMAC gel even smaller scale, but to like the agriculture kind of use. So this is the kind of parallel ways we wanted to have a better version as we develop more materials, better materials, more cost effective, but also working with a potential industry partner to see their needs. So I hope it's in next few years, not too long distance, so we can have some of these prototype devices for either water related or for agriculture related applications.
Thank you, Dr. Yu and Dr. Brannicky. We're really happy to have this presentation today, and really excited to see so many great questions and so much interest in your research. Congratulations again to you, Dr. Yu, on your award in engineering. We're also want to take a moment and thank Dr. Brannicky for hosting us today and moderating today's session. So we have a couple announcements as we conclude here, and let me just make sure that we've got everything set up. All right. So we have a couple additional sessions coming up for our other two awards recipients. The next one will be in 2 weeks on Wednesday, February 24th. Our O'Donnell Award recipient presentation for the Science Award. That'll be Dr. Benjamin Tu from UT Southwestern Medical Center. Will present on his research, and Dr. David Russell, a TAMIS member from UT Southwestern, will moderate that session. And then 2 weeks after that, we'll have the final research presentation from the Technology Innovation recipient, Christian Davies, on Wednesday, March 10th. And then 2 weeks after that, we have an information session about the awards nomination process. So if you're interested in nominating someone or have questions about the awards process, we have a whole session just dedicated to that on Wednesday, March 25th. And that'll be a really great opportunity to learn more about the process and answer any questions you might have about nominations. We're going to have slides and the video of today's session sent out to everyone in a follow-up email tomorrow. And you'll also get a survey at the end of this session for you to submit your feedback on the session. And just as another call for nominations, we have the awards nominations now open for next year's O'Donnell Awards, and would encourage you to nominate for the next class of Rising Star researchers in the state of Texas. Those nominations will close on April 30th. So once again, we'd like to thank all of you for joining us today. Thanks for your great questions. Thank you, Dr. Brannicky, for moderating today's session. And thank you and congratulations to Dr. Yu. That will conclude our session today. So please be safe, and we hope to see you next time. Thank you.